This is the basic RAS mapper window here. Whenever you create and run a plan, it will automatically be added to the results list. So I just ran this the other day, so I know the 2D 50-foot full equations result is good. When we add this to the tree list, we will create 3 maps for you automatically: depth, velocity, and water surface. There are lots of map types available to you. We're going to go through the full list here in a minute, but these 3 we find are the most important, and we're trying to clue you into, hey, this is what you should probably be paying attention to. All of these maps are dynamic. They're not created stored here, which means that we have the full power of the slider bar. So we can scrub through time and see what's going on. They're all responsive as you're using the slider bar. You can hit the max button to see what was the maximum depth here, maximum velocity. A note about the maximum for all of these maps is that the maximum is at the compute interval. It is not at your mapping interval. So when we throw this to the compute engine and they're looping through their really fine-grained time steps there, they're always tracking what the maximum value is, water surface per cell, flow or velocity per 2D face, that sort of thing. So when you see the max water surface here, for example, you may not actually see that exact value as you're scrubbing through time. This has to do with if you have a 10-minute compute interval and an hour-long mapping interval, you're getting 1 out of every 6 compute time steps when you go to the map here. So we have a 1 in 6 chance of actually hitting that peak value because we're only sampling it every 6th time to send it to disk. So if you see small deltas between max and that you're not able to reproduce in the time step, that's one of the strong reasons why. The velocity max is interesting in particular because it has some errors. We find it to be very useful still, but the time discrepancy of saying this face had a velocity at this point in time, and that was its absolute value highest, and a neighboring face had a similarly high value, they can not have occurred remotely at the same time. You'll see this a lot with tidal conditions or any water sloshing, where it might be 5 foot per second to the west for a while and then 5 feet per second to the east for a while, and you have 2 faces that just somewhat randomly decided that, oh, my maximum value happened to be when the water was going west, my maximum value happened to be when the water was going east, and they will cancel each other out because as we're rendering, like interpolating them, we say, oh, this face had 5 feet per second left, this face had 5 feet per second right, in the center, well, the velocity was basically 0. We know the maximum velocity wasn't actually 0 there. It's just taking pieces of information from 2 different points in time and creating an awkward interpolation. So as you're using these max values, in particular, maximum velocity has these kinds of egregious issues that you need to look for. So if you see hot spots, that's one reason for that. Another reason for that is wetting front instability. So if you have extremely shallow depths, and I just went to this section of the model yesterday and we confirmed that's what this was, but if you have extremely shallow depths on the wetting front, you have a very, very small amount of water here that's going to leak over this face. It will produce very high velocities for one time step here. Not really a big issue. If you get extremely high velocities that are for sustained periods of time, it could start to compound and get some model error. But when you have very, very shallow depths, less than 1/100th of a foot along here, it's going to happen on the wetting front. You're going to get small little spikes in velocity through your system. When we create the result file, we try to store everything that went into that result. So this is all of your geometry data, all of the event condition, precipitation, anything that is necessary to rerun it from inputs, we want to embed in the result itself. We find it to be extremely useful for the result to be a complete record of what happened. We could point back to the original geometry and say, oh, that's what we rely on. But your geometry is a living, growing, evolving entity. You're adding extra break lines all the time. You're expanding your model where it's deficient. So the result we find is a very good place to say, nope, we're pulling all the information in that it took to run it, and it serves as a record of what went into that run. So when we are interacting with the result, we're mostly going to be working with the geometry here embedded within the result, not the geometry that went into it. So with that, let's create a new map. We can right click and zoom to layer for any of these layers just to reorient, reset ourselves. And let's right click the result itself and say create a new results map layer. This is the map window that was in the slides there earlier. So it's effectively a 3-step process. First step, you select the map type you want. We can bounce through these and they'll have various different settings there. Most of them are just requesting that you pick the profile you want it at, but some of them, like arrival time, have other options. So let's pick a one that we don't have right now. Let's pick a Courant map. So if you're trying to check your model and see, was my time step roughly correct? One good estimation of that would be to look at Courant. Some of them, you'll see here, the maximum and minimum are grayed out here. It's because some maps we don't have maximum data for. It's something we're looking to expand because maximum requires either looping through the mapping interval and missing out on the potential maximum Courant, or asking the compute engine to store the true max Courant as it's running the compute engine. We don't have maximum minimum available for all of these yet. So let's pick a Courant map. Middle one's just a profile. Since it's a dynamic map, since we're going to be animating it, picking the profile doesn't matter here. We're going to use the slider bar for that. And then on the right-hand side, this is how we would like the map type that we would like, the output type. So up top, it says generated for current view in memory. This is what we call dynamic maps. So in particular, the top bullet point, the raster, is what we're going to be working with for most of these maps. The second one here is a raster based on terrain. This is your stored save to disk section. So if you're looking to produce a product to send to another GIS, that is what these group of bullet points is what you're going to be using. But for now, we're going to make it a dynamic map, and we're going to hit add map and then close. So Courant, as we're initially scrubbing through, you might say, hey, that looks odd. I know water gets into the system and I can see some amount of movement, even if I turn the mesh off here, but I can't really understand what's going on here. Well, Courant map, by default, we say if your Courant is sufficiently low, by default, we have a symbology that collapses to invisible, that has no opacity. So we could modify the symbology right here, set it to fully opaque, close it and say, okay, that looks a little bit more like what I expected. We have our symbology here in the lower right corner, so you can see it goes from 0 to 2. Okay, really, really low Courant values, at least at this point in the simulation. Another way that you can look at these overlapping color bars and appreciate the opacity a bit more, let's set this back to 0, so the Courant map collapses to an opacity of 0. Is you can change the terrain symbology in an interesting way. You can toggle off the actual color ramp and set it to a pure hillshade point of view. I find this to be extremely helpful when you're dealing with lots of conflicting high intensity colors here. If you're looking at multiple maps at a time, I find the terrain color ramp itself to be a little bit over the top and it's hard to make out what's what. Setting it to a pure grayscale with a hillshade background, really helpful for being able to scrub through this and then have a greater appreciation for, oh, that's why the Courant collapses to invisible, because that's not a region I really care about. Maybe where the Courant is closer to 0.5 or 0.7 down here, maybe that's something I need to zoom in on. The only region in the entire model here that, as we're scrubbing through time, that we can see is even above 1 is right where the levee is breaching. So you can zoom in here and say, oh, there's a couple of 2D cells. They're not actually that egregious. We can plot a time series here, does some post-processing, great. It gets a little bit above 1. Maybe we could lengthen our time step. Maybe we don't need a small of a time step. That would be something to experiment with. Oh, arrival time. When you create a new results map layer, like we were saying, some of them you're going to be forced to be stored. So inundation boundary, you're putting a polygon to disk, you force it to be stored. Arrival time is a little bit of an odd beast here. You will frequently want it to be stored because as models scale, this map type gets a bit slower. We have to scrub through all of time to make sure what's going on. This is a small enough model on a fast enough computer that I can have it generated in memory, and it works sufficiently well. It's not super fast, but it works sufficiently well to have arrival time computed in memory. But if you have a larger model, frequently you're going to want to say, oh, store that to disk. So all you have to do is hit the radio button over here and then add the map. The first thing you see when you create any stored map is that it happens instantly. You might think, hey, you guys are really fast at creating that. No, we're not. So the first thing you see is that there's a red asterisk and the stored saved icon here. The red asterisk you can get to by going to layer properties and, oh, we have a hover at one point. Sometimes the hover disagrees with the mouse. A different way to see it is if you right click that map, it says compute update stored map, map not created. So that was the error message that should have been in the pop-up there from the red asterisk. You can see, oh, I added the map, it doesn't exist. The reason we have this is because you can add multiple stored maps. And as you add those stored maps, you don't want to necessarily wait the 30 to 60 minutes for extremely large models that it would take. So you add them all at once, and then you can queue them all to compute at once and then go home and have a beer. But in this case, small model happens almost instantly. You can create the stored map, and this is what we're left with. This might be a good example here as I'm zooming in, what I was describing earlier about dynamic versus stored maps, as you get extremely close to the model and you see down where a terrain cell is a large portion of your screen, there are differences, and this might be easier if I toggle opacity a bit here. There are differences as we toggle the stored versus the dynamic maps here. The stored map has to produce a single value per terrain cell. That's why it gets to be blocky down at the lowest level. The error here should never be more than half of a cell because that's the maximum difference between the dynamic, the smooth answer, and the stored answer. As we were discussing in the lecture, you have a handful of maps here. If I'm looking to compare the maps from different results, if I've run two different versions of close to the same model, you can toggle both of them on, right? So right now it's rendering two different maps we can see in the tree view, and then go to parent, ultimate parent results node here, and scrub time steps that will synchronize the map types. You can see in the upper right corner is where we have the currently viewed animation time step. And then we can right click and say, well, let me plot a time series. So doesn't matter at this point what you have selected. It will look, you asked for a depth time series. Here are all the depth maps that you have on, and we're going to query them. Doesn't have to be the same geometry. Doesn't have one of them could be 1D, one of them could be 2D in this area, but we will query all of the depth maps that you have currently toggled on in the model and show you the difference. Can zoom in by clicking and dragging here, and all of the plots that we produce have a sidebar tables tab that allows you to see the tabular view of what's going on. One of the things that we found helpful, particularly in much larger scale models, is that water surface is difficult to get a sense of sloping while you're zoomed into a particular place in the model. So if I'm into this 1D area and trying to see, oh, which way is the water sloping or how steep is it? Really hard to get a sense of that from the base color ramp. And people were doing all kinds of weird stuff, modifying the color ramps anytime they moved around to a different portion of the system. We added some neat tools recently for that. The update legend with view allows you to, it changes your scale anytime you pan. So as we're panning through here, you can get at least a better sense of which way the water is sloping here. It's mostly useful for zooming into a very specific section of the model to try to suss out what the kind of smaller differences are there. Another way that you could achieve the same effect in terms of seeing local effects, sorry, I think this may have been off screen before, let's uncheck update legend with view, and let's say turn on contours. Any map that produces map values, raster values, can be contoured. So let's give it a very fine contour value of 0.1 feet and see how it looks. So you can see it's a little bit steeper down in this section of the river. It gets very, very flat here. And again, this is 0.1 feet. So even in this section, it's not that steep. If we were to hit the max button, and so this is the maximum water surface profile. and then zoom out, you can see, okay, really steep in the section of the river up here, fairly steep where the dam breach is, a little bit steep in kind of the choke point there, and then a much flatter area afterwards. One of the things that I discovered as I was going through this model was something extremely odd through most of the simulation here. So all of this looks relatively good, but I happen to know Muncie's pretty darn flat over here, and something extremely odd with steep water surfaces was happening over here. So we're going to bounce to 1 foot contour just to get rid of a little bit of the busyness. You should be saying, whoa, I'm going to check my terrain. Nothing really special about the terrain here. I was almost at the point of saying, hey, is the compute engine have a bug here that we don't know about? Turns out, no. This one was took a minute or two to suss out. Somebody, probably me when I was messing with it. No, probably not. Assigned an extremely high end value here. So when you're looking through the model, you might be bouncing in and saying, hey, I'm seeing kind of egregious water surface differences. We can use a profile line to say how egregious. Pretty significantly. That's a couple foot drop right here, just randomly with no meaningful terrain influence. There's not many reasons that could be happening, so pretty quickly should clue into, Manning's end values would be one of those reasons. And in this case, yes, somebody was mimicking a building by assigning a Manning's end polygon with an end value of 200 here, and that creates some odds hydraulic water surface effects as you're scrubbing through the system. Eventually it does fill in though, becomes normal. You guys have been introduced to the editing tools, but just one more time in case, you can right click your profile lines, edit layer. This allows you to go into edit mode where you can move profile lines around, delete them, add new ones. We're going to use the add new feature up here and then cross kind of a choke point of the system. Hopefully name that A. I'm going to stop editing and save. This profile line, we will scrape data from any geometry element you cross. It doesn't have to remain in the 2D area. It can go out of bounds and intersect the 1D area there. If we go down to plot profile, it'll look at the maps you have on. So if I were to turn velocity on, velocity would appear here, depth would appear here. So it reacts to the maps that you have on there. And we say plot water surface, we can see boom, this is the 2D section here, and it is 3 feet higher than the 1D section. Now, you might zoom in here and say, okay, that's weird. And it frankly is. Frequently, what this would mean is there is a levee in your system that isn't represented in the terrain. There is a structure here. When there are structures that bound these areas, we don't include that in the terrain profile. We're just cutting the terrain straight from the raster data. So hopefully there is a reason, or sometimes it's going to be a modeling mistake. I should have had a structure here that allowed overflow from one side to the other. Querying particular geometry elements, let's turn on the cross-section layer and the river layer. So you can right-click a cross-section. Like I was mentioning early in the lecture, anything that starts with results, we're trying to imply information is coming straight out of the compute engine. So this result profile plot of the water surface here is against, we will dynamically put the terrain under. You can change the water surface time step here and it will reflect in the map itself. You can see some point, yeah, it's reflecting in the map. Plot options. So on all of these maps, we have a variety of plot options that you can turn on. Hydraulic connectivity is one of the very useful ones. So as we scrub through time in 2D areas only, we can zoom in, and this shows us how water breached from one cell to another. So somebody had set up a break line here. There's a little bit of high ground. Somebody set up a break line. So we can turn on our hydraulic connectivity plot, back up in time a little bit. And in this case, it's a little bit obvious because the water itself is boiling over in the map. But in some cases, it can be extremely unobvious which part of the break line was pierced first. This hydraulic connectivity map with these blue lines say, hey, there's a blue line connecting these two cells. Therefore, water was sufficiently high to go from one cell to the other there. Really, really helpful for scanning your levees, scanning your break lines, and seeing did water eclipse the levee at an appropriate time. In particular, because sometimes there's just an extremely small amount of water in the corner. This blue line tells us, hey, there is actually water getting into the cell right now. It's just going to be an extremely small sliver here down in the corner.
Courtney missed the turning on the hydraulic connectivity, so maybe you could
Perfect.
turn that on.
Yeah.
One more time. Thanks.
So on any map, any water surface velocity depth map, any map that you have on, there are additional plot options here that reflect the water moving through the system, and the plot 2D hydraulic connectivity is, in this case, the top checkbox here. So I get to that by double-clicking the layer, just the convenient way to open up layer properties. You can also get to that by right-clicking and saying layer properties up at the top. So yeah, let's do a quick raster calculator demo here before we scrub out. So you can right-click a result, and right next to create a new results map layer, brand new option, create a new calculated layer. So opens up blank, but we are going to start in the upper left corner as one is meant to do and say plus button. Okay, pick a map, right? So this is the result that I'm currently working with. Great. I want a water surface map. Perfect. Let's do a water surface delta and animation behavior. Do I want it pinned to a particular profile, or do I want to be able to use the slider bar? So we'll use dynamic here and add variable, and I will call this WS1 for water surface 1. I added it. You can see it reflected in the output there, but it leaves the window open and says, hey, would you like to add another one? Frequently, it's not a very useful calculated layer if you only have one variable. So I'm going to swap plans here. So I'm going to go over to a different 2D 50-foot equation, NS. I don't actually know how it's different, but it's different. Pick the water surface map type, everything there, and I'm going to call this one water surface 2. So let's say NS stands for with n values for some reason. And I'm going to add variable here. It adds it to the layer list, modifies the output there, and then I'm going to close it. Now I've got two variables that I'm working with. So this comment up here is trying to describe what's going on with the calculator, but the actual code are these 5 lines right here. So you have a couple of variables that are available to you. In this case, no data is one of them. So I'm going to extend this to say it defaults to a small section of code that if water surface 1 equals no data, I am going to type in or else water surface 2 equals no data. If either one of them are dry, I can't really do a delta. Maybe I want to subtract a terrain value. So we could add a terrain layer here and do that, but we're going to keep it simple for now. Else output equals water surface 1 minus water surface 2. And just for grins, I'm going to add a error there because water surface 2z does not exist. And I'm going to say check code. One errors, view full code for more details. So if you hit the view full code button, it will tell you in a hopefully intuitive enough a way, hey, this line, this thing doesn't exist. So I'm going to close that, going to fix that typo and say check code. Perfect. And then create the layer. So this layer, we will, let's say it's probably no more than a 2-foot delta on either side. So I'm going to set the difference here from -2 to +2. Pick a better color ramp, and then zoom out in the system. So as I'm scrubbing through the calculator, you are seeing a live rendered view of the difference between one map minus the other. And let's go to someplace where it's more interesting. So most of the system, one of them is, they're very, very similar throughout most of the system, except right here, you're seeing an almost 2-foot delta. This happened to be where my Manning Zen was earlier, so maybe I wasn't too far off the mark with the difference between these two being this one section of Manning Zen. One of them is 2-foot difference or 1.5 feet different at this particular point in time. So hopefully you know more about your model than I do about the difference between these two results, but this is going to help you compare results effectively. Other small things in a remaining minute that I don't have, the particle tracing is very, very useful for toggling on. It's the little icon here with the particles going through it. You can modify these settings with this button, which brings up a little window here and say, hey, speed them up a bit. I've got a large model. One is not sufficiently fast. But they honor your time step, so I can scrub to a later point in the model and turn them back on, and you can see where is water flowing through the system. This is very helpful to plot depths, but get a sense of where water is moving through the system and how fast. So watch list is kind of similar to the raster calculator, really helpful for comparing results from two different models or from scrubbing data. If I turn both of these, or if I select this water surface map here and go down to the layer values, I can hit the plus button here, and it adds whatever my currently selected layer is to that watch list. Now I'm going to select the other result, and I'm going to hit the plus button once more. Now they're both here. I can add a string text value here and call this water surface 1. I can add a string text value here and give it a really descriptive name like water surface 2. And then I can scrub the slider bar to change the time step, and I will get a multiple series of returns here. I don't need both maps on. I can start to toggle these maps off, and I guess that's not super useful, but I can toggle the maps off if I get them to synchronize to the time that I care about and compare water surfaces that way. So it's a helpful way of taking any two layers. It doesn't even have to be a map. You can compare it or have the terrain always showing up there, but it's a helpful way to compare different values.